PA equals LU. This is our second example of an important matrix factorization that results from performing an algorithm on a matrix. In the last lecture, we studied EA equals R, which took advantage of the Gauss-Jordan algorithm, where we used elementary matrices to represent all of our row reductions. And then when we multiplied those together, we got EA equals R. Now, the way computing works sort of professionally is people care a lot about efficiency. And one of the problems with Gauss-Jordan and reduced row echelon form is that there's lots of unnecessary steps involved for lots of types of problems. So it turns out that if you want to do things like solve systems or calculate rank or things like this, the most efficient thing you could do is actually PA equals LU. So what is PA equals LU? In PA equals LU, well, this is a matrix equation where A is any m by n matrix, L is an m by m lower triangular matrix, U is an m by n matrix that's in row echelon form, so not necessarily reduced row echelon form, just row echelon form, and P is what's called a permutation matrix. So PA equals LU is maybe a bit more sophisticated than EA equals R in the sense that it involves more ingredients. And what we end up doing is reducing A not all the way to reduced row echelon form, just to non-reduced row echelon form. So I owe you an explanation of what a permutation matrix is, because this is one of the ingredients in our factorization. So a permutation matrix is any matrix you get by doing a bunch of row swaps on the identity matrix. So if you start with an identity matrix and do some row swaps, you get a permutation matrix. So here, let's build an example. So here I'm starting with a 4x4 identity matrix, and I am going to do some row swaps to get a permutation matrix. So the first row swap I'm doing here is row 2 switches with row 4. So I start with my identity matrix, and I switch row 2 with row 4. And if I wanted to, I could just call this thing a permutation matrix, but I'm going to do another one. I'm going to take the new row 1 and switch it with the new row 4. So I do that, and I get yet another permutation matrix. So the permutation matrix here that I've built, I'm calling P. So every time you do a row swap on an identity matrix, you get a permutation matrix, and if you keep doing row swaps, you get more and more permutation matrices. Now, permutation matrices are interesting for all sorts of reasons, but one reason they're interesting is that they're incredibly easy to invert. Normally, inversion isn't really difficult because you have to take your matrix, augment with the identity, and do Gauss-Jordan. But if your matrix is a permutation matrix, it happens to be an example of another type of matrix which is called orthogonal. And what that means is that the inverse of a permutation matrix is the transpose of that matrix. Inversion is hard, but transposition is easy. And so this is one of the reasons that permutation matrices are so simple to work with. So here's our first example of someone handing us a PA equals LU factorization. So, so here we have a permutation matrix P. So the idea here is that we started with the 3x3 identity matrix and did several row swaps until we got to this P. Here's the matrix A that presumably we started with from the outset. So this one is a 3x4 matrix. And so P times A here equals L, which is a lower triangular matrix, times U, which we see is in row echelon form. Note that this U is not in reduced row echelon form. For one, the pivots are 5, 9, and -8. And for another, the pivots are not the only non-zero entries in their columns. That's okay for non-reduced row echelon form. That's not okay for reduced row echelon form. So yeah, we see here L is lower triangular, and U is in row echelon form. Now, the reason we use the letter U is because every matrix that's in row echelon form is also upper triangular. So U sometimes stands for upper triangular. Now, just to illustrate like what you could do with such a factorization, one thing you could do is you could solve for A. Because the inverse of a permutation matrix is the transpose, I could multiply PA equals LU on the left by P transpose, And that produces A equals P transpose times L times U. So that's just not necessarily an important thing, but it is useful to remember that we can move P around our equation by transposing it. What about properties of PA equals LU factorizations? Well, one cool thing about PA equals LU is that U is a row echelon form of A. And what that means is that all of the things we care about when we talk about things in row echelon form transfer from U over to A. So if we're dealing with PA equals LU, it turns out that A and U have the same pivot and non-pivot column locations. So in our equation here, we have, I think this is a 4x4 permutation matrix multiplied by a 4x5A. And this equals a lower triangular 4x4 multiplied by a 4x5 row echelon form matrix. This row echelon form matrix has 3 pivots, and those are in columns 1, 2, and 4. So consequently, the pivot columns of A are columns 1, 2, and 4. What about non-pivot columns? The non-pivot columns of U here are columns 3 and 5. So the non-pivot columns of A are columns 3 and 5. Now, what do we do when we talk about pivot and non-pivot columns? Well, one thing we do is we use the number of these types of columns, or the numbers of these types of columns, to define the rank and the nullity. So if you have PA equals LU, the rank of A is always the rank of U, and the nullity of A is the same as the nullity of U. Now, this is useful because it's easy to figure out what the rank of U is. It's just the number of pivot columns. In this case, we have 3. And then the nullity of U is also easy to figure out. The nullity of U is the number of non-pivot columns, which is 2. So those numbers transfer over to A. So remember this picture that I really like. Our matrix A here is a 4x5 matrix. And so we can view it as a process that goes from R5 to R4. According to the rank nullity theorem, the rank of A plus the nullity of A equals the number of columns, which is 5. And the rank transpose theorem says the rank of A is the same as the rank of A transpose. So we also know that the rank of A plus the nullity of the transpose equals the number of rows, which is 4. Now in this example, we see that the rank of U is 3, so the rank of A is 3, and we can fill those numbers in here. We can use these numbers to figure out the nullity of A and the nullity of A transpose. Well, what number adds to 3 to get 5? That is equal to 2. So we know the nullity of A is 2. And what number adds to 3 to get to 4? Well, that's 1. So the nullity of A transpose equals 1. So I didn't have to do any work here because someone has given me PA equals LU. If I were only given A, I'd have to work somehow to figure out what the rank of A was, and then I could figure out the nullity of A and the nullity of A transpose. I don't need to do any of that work here because someone gave me PA equals LU.